Alright, silly people, here's the situation. We're going to be doing a code which does the over-relaxation method, um, which is a variation on the relaxation method where all that changes is instead of making your x equal to f of x, you instead make it equal to 1 plus omega times f of x minus omega x, um, and then update that as you go. And it's going to get to the value. It tends to get to the solution a little bit faster sometimes. Um, but the first part of the problem is actually to figure out what the error on the over-relaxation method is, starting by deriving an equivalent to equation 6.1, Newman says, which is evil because you don't need to start with 6.81. You actually just need to start with 6.75. So I did that here. You actually start with the equation that defines x prime, right? Um, and before he Taylor expanded f of x, so I did the same thing. I Taylor expanded f of x. And so after that, I distributed the 1 plus omega term through the Taylor expansion, only keeping the terms which, depend on the f of x star and f prime of x star, um, neglecting higher order derivative terms. So I get something like this, which I can solve for x prime minus x star in a form that was pretty nice. And so that's the equivalent of 6.75, which then you can go to page 256 and define x star like they did before in the book. Use this definition of x star on the left-hand side of the equation and use this definition of x star on the right side of the equation to get this equation with minus epsilons, which you can just divide the equation by minus 1 and you get your equivalent to 6.81, right? Um, and then after that, you set x plus epsilon equal to x prime plus epsilon prime using the solution for epsilon given by your 6.81 equivalent on the left-hand side and keeping the right-hand side the same, and then just chugging that along and solving for epsilon prime. I'll make it sound really easy. This took me like an hour. Don't feel bad if you don't get it right away. So the next part of the problem is actually to go back to the problem that we did, or go back to the equation we did in the last problem, x equals 1 minus e to the minus cx, and take that exercise, but also make it print out how many iterations it takes to get the solution. So this is that code. It only prints out the solution right now, but we can pretty easily modify it to also print out how many iterations it takes. We can just make a line here, set n equal to 0, and uptick n after every iteration by 1. And we can print out n at the end. So that's going to show us that it takes 14 iterations to get from x1 equals 1 down to the correct solution, right? So that's pretty cool. Then part C of the problem is to, again, now use over-relaxation method instead on this guy to see how many iterations it takes, and you'll see that it takes less iterations for this guy. So I'm just going to copy this code down, paste it into the next cell, and then modify it to do over-relaxation, which means we're going to need an omega. Newman suggests 0.5. We need to change this line. It's no longer x1 equals f of x1. It's now 1 plus omega times f of x1 minus omega times x. But you set x2 equal to x1. And we also need to change the error line. It's now 1 minus 1 over big thing in parentheses, which turns out to be, 1 plus omega. So in here, 1 plus omega times the derivative evaluated at x1, and then you subtract off from that omega, right? Okay, so that looks good now. We can print and show how many iterations it takes to get from 1 to that particular solution. And I already made a error. Oh yeah, this needs to be x1 here. My bad, my bad. But you can see that it gets to the solution accurate to 1e minus 6 in 4 iterations instead of 14, which is a really big improvement actually. So it's kind of nice. Are there any circumstances under which using an omega value less than 0 would help you find the solution faster? Yes, there are. If you have a function which varies like really wildly for just small values of x, then using a omega value less than 0 will actually help you quite a bit. It will make it so that the variation as you go from x1 to f of x1 is really small instead of however big it would be if you just plugged in f of x1. And so you can converge on a solution faster in that case if you have a vastly varying function. Right. I think that's good.